Now, limits are used to define continuity. You can talk about continuity at a point. So if we're going to talk about a two-variable function, f of x and y, we will say the function is continuous at the point a, b if the limit of the function as we get closer to a, b is equal to the value of the function at a, b. Now, this is no different than what we talked about in Calc 1. Now, remember, three things have to happen. You have to have a value of a function. You have to have a dot at the point. You have to have a limit. And then the two of them need to match. Now, you can talk about continuity on a set. We're no longer going to talk about intervals because we're talking about multivariable functions. We're going to say that a function f of x, y is continuous on a set D if it's continuous at all points in that set D. So this is just a natural extension of what we've done in Calc 1. But from these two definitions, what we can get are the following theorems. All polynomials in two variables, so some polynomial xy, are continuous in all of R2. There are no spots where a polynomial will be undefined. So that means if you ever want to take the limit of any polynomial function, you can simply plug in the value into that polynomial function. All rational functions in two variables, we're going to call it q of x and y, are continuous, not everywhere, on their domains, because rational functions have the possibility of being undefined somewhere. And that means that if you wanted to take the limit of some rational function, and remember that a rational function is a polynomial over some other term, and this can't be 0. We can talk about sums of functions, we can talk about differences of functions, we can talk about products of functions, we can talk about division of functions, we can talk about all scalar multiples of functions. All of these combinations of continuous functions are continuous on their common domains. So as long as the two functions you're adding, for example, are continuous, the result will be continuous as long as they're defined. Now, you can also extend it to composite functions. So if u is equal to g of x and y, and if this is continuous at a, b, and if z equals some function of u is continuous at the point g of a and b, so now z is a single variable function, then the composition f of g of x and y is continuous at a and b. By the previous theorem, if you now want to put a composite function over an entire set, all you can do is check the value of the continuity at each point in the set. So if I give you, for example, this function e to the x over y, and I say, where is this function continuous? Z equals e to the u is continuous for all real numbers u. This thing u x over y is continuous for all x being a real number, but y can't be 0. And that means then that this composite function, e to the x over y, is continuous for the set of points x and y such that x is a real number and y can't be 0. Another example of a complicated function, 3xy squared, x squared plus y to the 4. Now, this function is not defined at 0, 0, so this definition will be true as long as I'm not 0, 0, and then otherwise I'm going to assign the value of 0 when I'm at 0, 0. I would like to know, where is this function continuous? I can see that for all the points that are not 0, 0, this function is rational, and that means it's continuous everywhere on its domain. So it's going to be continuous for all points in R2 except 0, 0. And that means I need to answer the question whether or not it's continuous at 0, 0. So there are 3 things to check. Does this exist? Absolutely. It's been defined as 0 separately. And now what I need to do is talk about the limit as I approach 0 of this function. Does this limit exist? Now what we need to do is talk about the path that we're going to take to see if this limit exists. If I approach along y equals mx, that means the function that I have is now a function really of one variable. So it's going to be 3xy squared, x squared plus y to the 4. So this is going to end up giving me 3mx cubed. I'll have x squared plus m to the 4, x to the 4. So there'll be a common factor of x squared that I can cancel from the top and the bottom. And what I'll end up with is this result. Now, as x approaches 0, this function, x and mx, you can see from this will approach 0 as well. The limit along lines through the origin does exist. So no matter which diagonal line I'm going through, this will exist. But just because I've checked every diagonal line doesn't mean I've checked every single path. And in particular, if I were to talk about this parabola, a sideways parabola, so everywhere I see an x, it'll be a y squared, then the story changes. I'll have 3 times x times y squared. I'll have x squared plus y to the 4. Well, what this is going to give me is 3y to the 4 over 2y to the 4. So I'll get a 3 over 2. And right away, you can see that as y approaches 0, the value of this function goes to 3 over 2. So the limit exists, but it doesn't match. So if I'm approaching the origin along this sideways diagonal path, then I will have a limit, and these 2 things don't match. And because of this, the limit doesn't exist at 0, 0. And that means that f is not continuous at 0, 0. Note, if I've got functions that look like this, they are surfaces in R3. And because they're surfaces in R3, when they are not continuous, it's the same types of problems that you encountered in Calc 1. Sometimes your function could have a hole. Sometimes your function could have a break or a jump in its value. And that makes it not continuous there. Or sometimes you could have this volcano type function where it's an infinite limit. And functions that possess these kinds of things are not continuous.